let's say I want to know, let's say I got a population here. Okay, and this population has a cholesterol. This is a population. Average cholesterol for this population is 135. Okay, and this has a standard deviation of 5. I'm going to make up a relatively small number. We would expect 95% of the people in this population to have a cholesterol between 125 and 145. Make sense to everybody? 2 standard deviations above, 2 standard deviations above. What if I told you I picked somebody out on the street? I don't know if he's part of this population at all. I pick somebody out on the street and I test his cholesterol, and his cholesterol comes out to 150. Does it look like he's part of this population? No, it doesn't, does it? Right? Because he's quite a bit different. Even if I had gone to 95%, right? 3 standard deviations, that would be 120 to 150. 150 would be a very rare event to find someone with that high a cholesterol, right? So one of the things we can look at here is if I'm comparing this population to some other population, I can say to myself, well, how likely it is when I sample this other population that the result that I get is different than the population I'm working with here. Okay, so one of the important things here is that if we sample someone, remember this is a population, and I'm kind of like stretching this analogy a little bit for our purposes, but I think that 95% of the time, if I sample someone from this population, they're going to be between 125 and 145. Now, if I sample a person that I don't know if they're from this population and they come out to be 132, oh, there's a pretty good chance they're from this population, right? Because 132 is all the way in here. That's a pretty likely outcome for me to get if I sampled someone. Maybe 137. That's a pretty likely outcome as well. Well, how about 123? Well, 123, right? I will only get, remember this is 2.5% here, and this is 2.5% here, right? So if I'm looking and I say to myself, you know, if this is asymptotic, it really doesn't end. So I can't really ever say that somebody's different if I insist that like there's no chance of them, 0 chance of them being part of this population. Let's say that I'm willing to say they're not part of this population if there's less than 5% chance that they are. Less than 5% chance, all of the people that are out here are so far out, they're only going to happen 5% of the time, 2.5% on the low end, 2.5% on the high end. So if I get a value less than 125, less than 140, I'm going to say, you know, I think there's a pretty good chance that person's not part of this population. And my chances of being wrong are less than 5%, because that's how likely this is to occur at that extreme. Well, you'll never notice that a lot of studies say, well, the p-value was less than 0.05. It's a little bit more complicated because they're dealing with samples, not individuals, right? So it's a lot more complicated than that. But that's why you hear the word 95% confidence interval, a p-value of less than 0.05. What you're doing is you're not relying on a study to be big enough to be absolutely certain, because basically you're never going to be absolutely certain. No matter how big a sample you take, you'll never know what the true sample mean of a population is. Why? Because you got to sample the entire population and know it. Any sample you take is going to be a sample mean, right? It's never going to be for sure what the true population mean is. So you're always going to say to yourself, I'm willing to be certain within this range. And that's typically 95% certainty, or less than 5% chance of being wrong. And that's why a lot of studies, when they're published, someone else tries to replicate them, and they find, oh, well, wait a second, we can't replicate those results. Because by chance, they happen to get a sample that was outside of that 5% chance of being wrong, right? So you're never really certain when you do these kinds of studies. but at least you know how uncertain you can have a measure of how uncertain you are. Okay, so now let's get to binomial distributions. Okay, so I hope I confused the guys online as much as I confused you guys at this stage with that. That makes sense, though, right? Because you do see that come up quite a bit, confidence interval and so on. So let's talk about binomial distribution. Okay, so I'm going to take an example here where it's going to be something that's going to be kind of like the result of that fancy factorial formula that you looked at before. Okay, all right. So I'm going to say, let's say that the probability that a person is left-handed in this population is equal to 20%. Okay, I'm going to sample 10 people randomly. Now, what are the possibilities for a number of people that could be left-handed if I sample 10 people? What's the minimum number of people that could be left-handed? How many? Well, the average number of people, my expected value, not expected value, but the most likely value is going to be 2, right? Right? Remember you saw that before. The mean was mu times p, right? So p times n, rather. Okay, so our sample size is 10, right? And our probability of any single person in that population being left-handed is 20%. Okay, but if I sample 10 people, the minimum number of people that might be left-handed is 0. Maybe I get a sample 10 people, nobody's left-handed, right? That can happen, right? Or it could be 1, could be 2, could be 3, could be 4, could be 5, could be 6, could be 7, could be 8, could be 9, could be 10. That's all of our possible outcomes. For our probability tree, remember our probability tree? These are all the possible outcomes for 1 out of 10 or 2 out of 10 and so on and so forth, heads or tails or whatever. In this case, left-handedness. Okay, so if I ask you, what's the probability of exactly 2 people being left-handed? Well, the way you could calculate is you could get that formula and say, oh, n factorial is 10, n factorial is 10 over x minus n, which is 8 factorial. You'd have to go through that whole formula with the powers, to the power of 10, the power 8, and so on and so forth. You'd have to use that formula to calculate it. Well, fortunately, into Excel, we have built in a calculator for binomial distribution. Equals binom dist. And again, just like before, I put the parentheses in, and it comes up with the arguments that it wants me to fill in. I'm going to read them for you because they're really small. Number S, that's number of successes. What's a success in this case? A success is someone that's left-handed. No, not a number, but a success is any person that's left-handed. If I pick 10 people, any person that's left-handed is a success, right? What's the number of trials? Number of trials is the number of people that I sample. In this case, 10. Okay. What's the probability of success? Probability of success for any individual person is 20%. Probability that they're left-handed. Notice that it's always got to be the same for every person. Okay. And then I got that nasty little word cumulative again, where I have to answer true or false. Okay. So this time I'm going to fill this in. Number of successes is going to be, notice I put it next to the 2, the most likely outcome, 2, comma, 2, comma, number of trials is 10, comma, the probability of success is 0.2, comma, now cumulative. Well, you want to know something. What was the question I asked? What's the probability of getting exactly 2 out of 10 that are left-handed? Oh, well, gee, I don't want that to be cumulative. I just want that result. So now for this function, I can use false. And when I use false, it tells me the probability that I sample 10 people get exactly 2 out of those 10 that are left-handed. How about 1? What's the probability that I would get 1 person that's left-handed? Okay, that's going to be binom dist, parentheses. And this time I'm going to put the number of successes is going to be 1, comma, trials 10, 0.2, comma, and false. not cumulative. Okay, that's 26%. It's a little less likely that I would get one person that's left-handed than two. Makes sense, right? 20%, I would get that, but it's close. How about 0? Binomial Dist, parentheses, 0 successes out of 10 trials. 0.2 is the probability, and false again. That's 10%. 10% chance I'll get none. That's not that big a surprise because there's only 20% likelihood. Yes. I'm sorry, say it again. Why the probability is that's the probability of success for any individual in that group. Remember I said that the probability of being left-handed is 20%. Right, that's where the 0.2 is. The probability of success, meaning that one of those people, that person is left-handed. Okay, so you want to know something? Let's test this idea of saying true. I'm going to go over here. I'm going to say equals. Well, first of all, number one, if I ask you, what's the probability that I would get 2, 1, or 0, 2 or fewer people that are left-handed if I sample 10 people? Well, it's the sum of all these probabilities, correct? Okay, so it's going to be equal to the sum of this probability, and this probability, or the probability that you would get 2 or fewer people when you sample 10 from this population where 20% are left-handed is 68% roughly. Right? That's the probability. Probability you would get more than 2 is going to be 1 minus that. Right? Kind of cool. But now watch this. Remember that thing in that cumulative trick? Okay, let's try that. Binomial Dist, parentheses. Okay, and let me just spread this out a little bit. Parentheses. Okay, what is that again? That's going to be, let's see, 2, comma, 2, comma, 0.2. I'm sorry, trials is 10, comma, 0.2 is the probability of success for any individual. And this time I'm going to say true. What's going to happen now, it's going to give us the accumulated probability for 2 and lower, which we just found was 67%. Okay, hold your breath. Comes out the same thing. That's what saying cumulative true set does for us, right? And we know that 1 minus that would be 3 or more, right? Now I'm going to just do something quickly. On this one, I'm going to say equals binomial Dist, parentheses, and I'm going to say this time instead of x, I'm going to put the number, C5, comma, trials is 10, 0.2, and false, right? That's going to give me the probability of exactly 3. And then I'm just going to drag this down to do the calculations all the way through. And you notice that the probability, because it's only 20% chance, right? The probability of getting 10 out of 10 is 1 times 10 to the minus 7. It's like 1 in 10 million, right? Very unlikely. Okay, so if I add all of these probabilities up, what's it going to come out to? Did I hear 1? Somebody say 1? That's what it comes out to. It comes out to 1. Exactly. Now you might get a problem where you're asked, what's the probability that you would get 4 or more people that are left-handed? Well, you can't do that with this function. You can't do 4 or more. You got to do 3 or less, and then subtract it from 1 to get the probability for 4 or more. How about if I give you guys an example that you can try, and then we'll call it a night. Okay. How about let's say that 35% of the people in Hunter wear glasses of one kind or another. If you randomly select students at Hunter, you take a sample size of, say, 20. What's the probability that you would get 5 or fewer people that are wearing glasses? Okay, so the number of successes is equal to 5 or more. Okay, remember, this is a little tricky because you're not going to use 5, right? 5 or more, and the number of trials is 20. And we're just sampling 20 people. Okay. And you want to know what's the probability that 5 or more are going to be wearing glasses. The probability of any individual person wearing glasses is equal to 0.35. Okay. Oh, you guys are online. I think you're keeping up. It's really a two-step problem, right? If I had said 5 or fewer, it would have been a one-step problem. But saying 5 or more makes it a two-step problem. We're in session 4 now, right? Next week's in session 5. We'll be after next week. It'll be a third of the way through the semester. Flies, right? Time flies. I'm going to wait for a couple of faces to kind of like pop up out of the computer so I can give it a try. Okay, let me just go over this so I can get you out of here on time. Binomial, so 5 or more is what I'm interested in, right? The only problem is this only works cumulatively from that number down. So instead of calculating the probability of 5 or more, I'm going to calculate the probability of 4 or fewer. 4 successes, comma, 20 trials, comma, 0.35 is the probability for any individual, and true. So this is going to be the probability of getting 4 or fewer people. And that comes out to be about 12%. So the probability that you would get 5 or more people is going to be equal to 1 minus this number. Whoops. Minus this number is going to be about 88%. Right? That's simple. Got to be a little bit careful about the wording. If I had said more than 5, what would you have used instead of 4? You would use 4 to figure out 4 and lower so that you got 6 and more. But if I said, what's the probability of more than 5, that would really be 6, 7, 8, 9, so on and so forth. So you use 5 or fewer on one end and then subtract it from 1. Yes? You use true. When you use true, it gives you the probability from that number that you put in the first number, 4, number of successes, for that number and fewer. So in other words, if I put in 3 as the number of successes and say true, it'll give me for the cumulative probability for 3 out of 20, 2 out of 20, 1 out of 20, and 0 out of 20. If you say false, it will only give you the probability for exactly getting 3 out of 20. Okay, just like we did here. Okay. All right, yes? No, it doesn't. Yeah, no, it only goes that direction. As far as I know. That's well. Why is the table always just to the left, right? So, I guess that's just the way they designed the function. It would be nice if they dress these up a little bit or something like that. I'm using just the basic functions that are in Excel because there's an issue with the Mac. They used to have it in Microsoft had MS Basic or something like that. They had a different name for it. I forget what it is. All of these were programmed in that language. A lot of the extra functions. And when they upgraded the Mac in about 4 or 5 years ago, they didn't put the compiler for that language into the Excel version. So a lot of add-on packages that work on the PC don't work on the Mac, right? So I try and just stick to whatever the basic functions are, because then I know everybody's got, and some of the older versions of the PC don't have certain functions. So I try and stick to just the basic versions that I know you're going to have on your computer. Now, as far as every once in a while, you'll see like several choices for binom.dist or binom dist or whatever. Some of those are just updated versions of the same function, and functionally they're really the same.